Okay. So I'm starting unsupervised learning today. I put what we're doing today because this was originally going to be everything, 6 hours worth of content, but now it's about 4 hours. Okay. So here's what we're going to do. I'm just going to do an introduction to unsupervised learning, some applications of it, why you might want to do unsupervised learning, and also why you might want to not do unsupervised learning and go with a different alternative. And then I'm going to go through this kind of quickly just because, I don't think it's what really anyone likes. It's more like you just kind of have to get over it with looking at the examples and stuff. Like most people probably skip it. And then I'm going to look at calculating how you can calculate the similarity between two elements. So comparing how close they are together, what inertia and WCSS is, and then finally we're going to get onto k-means and k-means plus plus. So feel free to put any questions in the chat and I'll periodically check. Okay, starting with the introduction to unsupervised learning. So what is it? So in supervised learning, you have labeled data and you want to find a relationship within the data, which will let you predict future unseen data values. So you might have like a linear line or something, and then you can, based on your x, you can calculate a y, something like that. But you can't do this in unsupervised learning because you don't have this labeled data. So if we look here, down here, we have all of these points here. It's been labeled already, and these ones haven't been labeled. In unsupervised, it's all unlabeled. So rather, in an unsupervised data, we have unlabeled data, and we want to find patterns within the data. So this can be done through clustering or dimensional reduction. So clustering is looking at this data here, and we can see there's groups. So we've got a group of 4 here, group of 3 here, group of 5, and a group of 6. And this is done because these should all have similar traits. So that's clustering, and then we also have dimensional reduction, which is going to take something like a 2D dimensional thing and turn it into 1D. Okay. So the main thing is clustering, dimensional reduction. We'll touch on it a bit because you use it a bit in clustering. So where do we see clustering? So Google News. We can have clusters of like articles. So when you're in one article and it wants to recommend you more, in those similar topics that you might be interested in, market segmentation. So here we've got a bunch of people and their income and age, and we can see there's clear groupings here. So like here, if they're older and also they have a higher income, they're executives. Well, I can't read what it says, but this would be maybe lower down jobs within the company for younger, lower income people. And dimensional reduction is going to take something and lose its data, which might not be important data, and it's just wasting processing time and storage. So here, I'm not sure how these images are being stored, but we can see here is 400 dimension. It's 400 dim, so 400 dimensions. Not sure how it's been stored, but it's not really matter. And we can bring this down 10 times to 10 times less dimension, and we still have pretty much the same image. So we've saved on 10 times for storage here. Oops. Okay, so dimensionality, we're mainly looking at clustering, but clustering also has a bit of dimensionality reduction in it if you want to, but we'll see that later. So why would we want to do unsupervised learning? Is because the data is abundant and cheap compared to labeled data. Everything is by default unlabeled, so we can use that for unsupervised learning. But if we want to do supervised learning, we have to go out of the way to get labeled data. So it's going to be a lot less of that, and it's going to be more expensive. With dimensional reduction, which we had back here, we can reduce the noise. So some of the data might not be necessary, so we reduce the dimension to save on the storage. And also when processing, if it's not important, that's just more calculations we have to be doing, so we can save on computation. And also dimensional reduction can be used as a pre-processing step for supervised learning. So although it is unsupervised learning a characteristic of it, you might still do it as a step before supervised learning. And here's why not. Why you might not want to do unsupervised learning. You might want to do supervised learning or something else instead. So there's no simple goal. In supervised learning, we're clearly finding a relation to predict like future values with it. Here, we're finding clusters, but it's not clear what we want to do with that. Or with dimensional reduction, what's the end goal of it? It's not as clear. And also validating our results is going to be subjective. In supervised learning, we have the cost function that is going to return a value, and we want to minimize that as small as possible. It's not so clear in unsupervised learning on how we can judge the performance of our model. Okay. Yeah, so that's for just this top bit. Just don't know that quickly. That's just kind of the start of the PowerPoints. Is just why we're doing this. So what we're going to be mainly looking at today is clustering. And the goal in clustering is going to be finding natural groupings in our observations. So if we start here, if we ignored the colors, we've got the dots, we can see there's 3 clear clusters. Of course, it's subjective. Like sometimes you might think that's here, if they're closer, it might be in the middle, you're not so sure. But generally what we want to do is we want to segment our elements such that they have high intercluster similarity, which just means high as in similar inter, so inside the clusters, they're nice and close together. And the formal way of saying that is the high intercluster. So high is in close, inter within. And then the opposite is low similarity across clusters. So low, now instead of inter, it's intra. So across these clusters, they're not so similar. So we can see the center of here and the center of there, they are far apart. So these are just keywords that you need to learn. Okay, next we need a way to define how similar 2 items are. And the way that we do this is by converting our data into vectors. So here we've got 5 animals and we've got some information about them. So a badger, I don't know what most of these mean, but we can see it's 3, 1, 3, 1, 10. So we convert these into vectors. So we got badger is 3, 1, 3, 1, 10, and a bear is 3, 1, 4, 2, 2, 7, 8. If that's okay. Do you mean high intracluster? Oh, sorry, did I mix them up? Yeah, that would make more sense. Yeah, so low. Yeah. Wait, is it wrong on this diagram? I took this diagram from Google. This should be high intracluster. And low, yeah. Wait, is it? Are you sure? Is that not what I wrote originally? High intercluster. Oh, distance. I see what you mean, sorry. Yeah, so high intercluster distance. So the distance is high across the clusters, and within the cluster, the distance is low. Yeah. Okay, so we've got 2 vectors here. So we saw badger is 3, 1, 3, 1, 10, and bear is 3, 1, 4, 2, 2, 7, 8. So we could do a dimensionality reduction here. If, let's say, some of the data is irrelevant, let's say the weight is irrelevant to the model or how we want to be clustering these animals. So we can just ignore this or cut it out if it's not important to us. But we also need to consider sometimes the values might not be numbers. And the way we do that is if we have nominal feature attributes, we'll need to convert them to discrete values. For example, if one of the features was like its size and it said small, medium, or large in our data set, we're just going to map small to 1, medium to 2, large to 3, like that. And now all of it would be numbers, and we can now do the maths on those numbers. Okay. Next, we need a way to calculate what's called a proximity in, I think this is indice, which quantifies how close two vectors are together. So right now we've got these vectors, so badger and bear, and we want to be able to say how close are these, how similar are they. So we need to pick a distance type, Euclidean distance, Manhattan distance, and Chebyshev distance are the three most popular ones. So we're going to be, mainly we look at Euclidean distance, which is like Pythagoras' theorem and like that. And what I think is, when they just shove the equation at you, it makes it seem scarier than it is. So I'm not going to show the equation straight away. We're going to look at the logic of how it works. Okay, so Euclidean distance is basically just Pythagoras, but for more than 2D. So we know in Pythagoras the distance is going to be the square root of a squared and b squared. A squared plus b squared, square rooted. So this is just a squared plus b squared equals c squared, rewritten, and then I've just, instead of c, I've put d. And if we wanted to do the same thing in 3D, all we're going to do is we're going to do Pythagoras once, and then we're going to do it again. So if we wanted to calculate AD in this 3D space now, first we can do Pythagoras from b to d, which is going to be b to c squared plus c to d squared, and then that thing square rooted. And then we just do it again, now with a. So we've calculated this, sorry, I can't think of a word, not horizontal and vertical, but of the diagonal line. We've calculated this diagonal line. And then now we do Pythagoras again with this vertical line. So that looks something like this. Like this. So we've got a squared plus b squared. And then we take the square root of that for this distance. And then we end up squaring it again. And then doing plus c squared. And then square rooting that again. And what we'll see is this square root will actually cancel out with this square. So in the end, we get the square root of just a squared plus b squared plus c squared. And this is going to work for any dimension. So we can, let me go to the next slide actually. So this works for any dimensionality. So even though we can't visualize a 4D kind of graph, we can still continue this logic. And if you continue doing it every time, it will just cancel out. And we'd get a squared plus b squared plus c squared plus d squared, all of that square rooted, to calculate the distance between those 2 points in a 4D space. And then next, all we need to do is, rather than having rather than having A, B's, and C's, we just need to take the absolute of the values subtracted. In Euclidean distance, it doesn't matter. So rather than having a squared, the distance between 2 points is going to be just one of the feature vectors subtracted the other feature vector. If you're doing Chebyshev distance or Manhattan distance, you then want to take the absolute, so you always have its positive value. But here, because it's Euclidean, you're squaring the values every time. It doesn't matter if it's negative or positive, because like minus 2 squared is the same as 2 squared. So in the end, you get this equation, and all we're saying is the distance between the distance between two vectors, so this is x1 and x2, is just going to be what we worked out here, just the square root of just the distance between each individual vector within it. Would have gone hard if that door swung open. Oh yeah, yeah, we'll see this coming back. Yeah, so we're just calculating the distance, squaring, adding them all up, and in the end you get this equation. I don't like how on the PowerPoints they just give you the equation because they look more complicated than they are. Yeah, so mainly we're doing Euclidean distance, but there's also the Manhattan and Chebyshev distance. So Euclidean, it's just Pythagoras' theorem, pretty much. So you do 3 squared plus 4 squared is 25 and square root it to get 5. Manhattan distance, which is just you're not allowed to walk in diagonals. The closest way from here to here, you're either going to go 4 to the left and 3 up, or 3 up and 4 to the left. In the end, you end up walking 7. It's 7 distance away, 7 meters, whatever it is. Finally, Chebyshev distance, you take the maximum of the dimensionality differences. So if you had 5 feature vectors, you just look at the difference between each of them and you just take the biggest one. Okay, so does anyone know there's 4 distinct properties of distant measures which are true for Manhattan, Euclidean, Chebyshev, and also any other ones? You guys know them? Okay, that's fine. So one of the first ones is the distance between any 2 points is always non-negative. So it's either 0 or greater than 0. We can't have negative distances. So we can see this is going to always be true in how we calculated these, because these two we took absolute Euclidean distances squared. You can't, after you square a number, it's always positive. We also have a distance between itself and, a distance between a point to itself is also always 0. Which makes sense. If you're at a point and you want to get a point, you don't have to go anywhere. It should be 0. And that, obviously, that works for Euclidean distance, Chebyshev, and Manhattan. Another point we have is the distance measure is symmetric. The point A to B is just as long, or takes just as long as B to A, because they're mirrored. So, obviously, and it's not negative, so we're not like doing, I don't even know, like displacement here where it can be negative. We're doing distance. So x1 to x2 is going to be the same as x2 to x1. And the final one is the distance measure satisfies a triangle inequality, which means, so this is kind of like in Pythagoras' theorem, I don't know if I have a diagram, going directly to x1 to x2 is going to be shorter than going x3 and then x3 to x2. It's because the hypotenuse is always shorter. And we can see that here. So 5 is shorter than going 4 then 3. Does this all make sense? Okay, one final thing we need to look at is just feature scaling. This makes sure that all features contribute equally to calculating the distance or calculating the similarity between 2 points. Because if, let's say, we had one feature that scaled between 1 and 3, and then we also had another weight thing, and it was like 7,000 kilograms. If we don't scale our features, the 7,000 kilogram one is going to have a lot more weight than this other feature, and that might not be a fair representation of our data. 2 well-studied approaches are min-max normalization, this is what we use, and also z-score standardization. But I don't think we ever looked at z-score standardization other than just its name and knowing that it exists. What we mainly look at is min-max normalization. Okay, so how do we do this? So we do this by rescaling each value so it's between 0 and 1, where 0 represents the previous minimum, 1 represents the previous maximum, and everything in between is scaled correctly. Formally, we would write this like this, where we say its new point, so xj, its new point. I don't know why they use j here, but the new point is we take its value, we subtract the minimum, and we divide that by the difference between the max and the minimum. And in the end, this scales it. So if we previously had 3, 5, and 7, our previous minimum was 3, our previous maximum was 7. So these go 0 to 1, and then 5 is in the center of these, so it would become 0.5. And if we, let's say, had 6 as well, this is going to be 0.75. So now everything is scaled between 0 and 1. Okay, we're gonna do this together because it's kind of quite a lot of work doing it by yourself, so we can do it as a group. And we want to work out the Euclidean distance between cow and dog. So we're trying to see how similar these two are. And first we need to scale them. Okay. So for cows in scissor, what would this be scaled? And how can we work that out? Would all threes be 1? Yeah, so the minimum is 0. Hi, here's Ash. Yeah, so the minimum is 0 in scissor, and the maximum is 3. So 0 is now 0 in the new one because it's the minimum. 3 is now 1 in the new one because it's the maximum. And here we don't have any in-between values. So if we normalized all of these, it would be 1, 1, 0, 1, 1. Okay. K9, what about this one? Yep, exactly the same. It's already scaled between 0 and 1. 0 is the minimum, 1's the maximum, nothing's going to change. What about molar? Four is 1. Yeah, so we need to remember the minimum here is now 3. So these turn into 0, and 4 turns into 1. Yep, so that's right, Victor. I don't know what you mean, Ash. Well, the 3 scale to 0 because they're the minimum. We have no in-between values still, so it's still 0, 1, 0, 1, 1. Oh yeah, 3 is, yeah. Okay, what about premolar top? This one's a bit more interesting. What will these be? One is 0, 2 is 0.5, and 3 is 1. Does anyone disagree? Yeah, I think Victor's right. So yeah, so the minimum is 1, so that turns into 0. 3 is now the maximum, so that's 1. And the 2 is right in the middle between the 1 and 3, so that gets 0.5. So we got 0, 0.5, 1, 0.5, 0.5. Okay, well, I just lost this line. Okay, now we come to weight pounds. So this one's a bit more complicated, so let's just, yeah, I don't have a calculator on me, but that's fine. But what's the minimum here? 5, and the maximum 400. Yep, so everything's going to be scaled in between there. So let's just see. So we're looking at cow and dog, which is, so 400. We know that one's going to be 1, and we know dog's going to be, what will dog be? We're going to have to do 20 minus 5 divided by 400 minus 5. 5 divided by 400. Oop. And this is just our equation from earlier. 20 minus the minimum divided by the max minus the minimum. So this one's scale turns into this. 15 over, yeah, that's right. Okay, so how can we calculate the Euclidean distance then? So we've worked out each of these, normalized. So what's the next step? So if we look at our equation, wherever we had it, we're going to find the difference between each one and just add them all together. Find the difference between each one, square it, and add them all together. But at the end, we can just take the square root. So here, the difference between cow and dog, when it's normalized, it was 0 and 1. So it's 1 squared is just 1. 1 squared again, just 1. Here we had 0. Sorry, this is 0. This was 1. 1 squared again. 2 and 3. The difference between this is going to be 1 and, so it's the difference between 1 and 0.5. So that's 0.5 difference. Sorry, 0.5 squared. And then this number squared. So we have 1 squared plus 1 squared plus 1 squared plus 0.5 squared. Is that right? Is that correct? So we just want to take this and also square root it because we have to take the square root at the end. So we took each of these, the difference between them, squared them, and then square rooted it at the end. Let me know if I made a mistake there. Yeah, okay. So this is, what did we call it? The proximity indice. So we've just calculated the difference between cow and dog. When you're actually using this for practical reasons, you would be calculating the difference between cow and everything else, and also anything else in between them. And then you can now use this value. Now, this value by itself here doesn't really mean anything, but it's going to mean stuff if we're using it to compare it to other values and see how is a cow and dog similarity compared to a cow and a badger, for example. Okay. And now we need to go on to clusters. The first thing we need to know is how to calculate a cluster centroid. It's quite simply done. We just take all of the points within this cluster and average them. So if they only have 2 points each, we just take the average of their x and y, and then it would work in 3D space and also in 4D and any high dimensionality as well. So if there's 3 points in cluster 1, we're just going to average each feature vector to get its center. So if we were here, also by the way, sorry, I didn't write this here, you do this after the normalization as well. So if badger and bear were in a cluster, their average for their incisor, so their first feature vector, is going to be 1. So it's 1 plus 1, average, there's 2, so that's 2 over 2. And we get an average of 1. And then we do the same for K9. Average of 1 here. Average of 0.5 premolar. Average of is 1. Sorry, this goes to 0. This goes to 0.5. Average of 0.25. Weight in pounds, you would scale them and then average them again. Okay, so now we've got a cluster and we know how to calculate the center of a cluster. We need a way to measure how compact our cluster is. And we do that through this thing called inertia. And the way we calculate the inertia of a cluster is going to be taking the square of every distance between every element that's in the cluster to the center of a cluster. And remember, the center of a cluster is the average of all of the elements in the cluster. So if we have 3 items in our cluster, we're going to calculate their individual distances from the center, square it, and sum all of them together. And the way we write this formally is by doing sigma, so sum of, for every element in our cluster. We're going to do the Euclidean distance. Here you could do a different distance type if you wanted to, or if you were told to. So we're summing for every element in the cluster the Euclidean distance between the element and the centroid and squaring it. And also important that this square is not squaring the sum at the very end, you're summing it as you go along. So for every element, calculate its distance to the center and square it. And this inertia tells you how compact the cluster is. And you get it because of the squared. Because as it gets further out, it makes more of an impact. If that makes sense. Finally, sorry, not finally. I don't know why we're saying finally. With it, we need to define the within cluster sum of squares, which is simply every single cluster, we just calculate its inertia and just sum it all up. Simple as that. So for every cluster in C, sorry, this like weird C, which I think is I can't remember the specific name of it. The clustering structure is this weird looking C. So for every cluster in the clustering structure, calculate its inertia and sum that all. And the reason we have that is because we want to be minimizing this. If we want to have the best clusters possible, we want them all to have the smallest inertia, because the inertia is how compact they are. So we want them all to be as compact as possible. And that's called the WCSS, the within cluster sum of squares. So we have an optimization problem now, and we can say we want to minimize WCSS, which is our inertia sums. And also, the way they write it here, it looks complicated, and all it's saying is every element belongs to a cluster, and no one element belongs to two clusters. And the way they write it is like this. So we want to minimize WCSS, so we're just minimizing our inertias, so every cluster is as compact as possible. And we also say such that C1, so our first cluster and our second cluster, our first cluster or our second cluster, or every single cluster, is every single element, so every element belongs in a cluster. And also, this says one cluster and another cluster is empty. There's no two, which just means every element belongs in at most one cluster. And also, so we're saying it belongs in, every element has a cluster, and also every element only has that one cluster, pretty much. And that's just the formal way of writing it. But this is a hard problem. If we have 100 elements and we want to partition them into 10 clusters, that's 10 to 100 combinations. So this number has 100 zeros. It's a big number. We're not going to be able to brute force. We're not going to be able to try every combination and work out all of the inertias and then just pick the minimum WCSS. That's not going to work. So what we need is a heuristic algorithm, which I don't think we use this word in uni, but this is what we used in A level. Which I used in A level, which means our algorithm might not be optimal. It might be slightly less. It might be 5% suboptimal. However, our heuristic algorithm is going to compute it in a reasonable amount of time. It's better to have a suboptimal solution than an optimal solution that won't compute for 7 quadrillion years. And one such algorithm is the k-means algorithm. The k-means algorithm is quite simple. I'm going to show this. I found this animation which I think shows it quite well. And all you do is you pick k random elements, make these the centroids, assign each element to its closest centroid, and then recalculate each centroid's center and repeat that from step 2 until we're satisfied. So I've just got this animation here. The one thing they do differently is they're not picking a random point as the centers of the clusters. They're just doing some random out here, so that's the only difference. So let's just see how they do it. So we can see if we have a point here, right now, we only have one center. So of course, every element is closest center. Sorry, is closest cluster centroid is this one. So let's just say we have k equals 3. So we make 3 clusters, so 3 random points. So that was part 1. Pick 3 random elements as their centroids, or here, they've just done 3 random points on the board. Okay, the next step, assign each element to its closest centroid. So here you can see they've coloured in the backgrounds, which represents if a point is in this background, its closest is blue. So we can see its closest is the yellow here, and when we go over here, its closest is blue. So the next step is assigning every element to its closest centroid. I think I'll do soon. So here, all of these, its closest is blue. All of these closest are red. And here, this kind of cluster of elements here, it's kind of split in the middle. Some of them are closer to blue, some are closer to green. Okay, so that's part 2. Assign each element to its closest centroid. And then now we just need to recalculate each centroid's center and repeat from step 2 again until we're satisfied. So now that we've assigned all of these elements to this centroid, we can recalculate the center. So in here, we've now moved it to the average, so we can see the red has pretty much moved straight into its center of all of these elements. Blue is slightly skewed to the right because some of these, we also have to include these ones in our calculation. So the average is between these 2 clusters. And green has just moved down towards its center of here. Okay, so that's part 3. We recalculate each centroid center, and then we just repeat it again. So now we reassign every element to its closest one. So these are all still the closest to blue. These are all still the closest to red. And now these ones, because the blue's moved quite far away, because it's been moving towards these ones, because it was the average of these 2. These blue ones have now came into this other cluster. So now we repeat it again. So we assign all of the elements to their new clusters. And we can see these have stayed the same, but now these original blue ones have turned into green. So we've done step 2 again, and now we recalculate every centroid center. So blue's moved further into the center of these, red's stayed pretty much the same, and green's moved a little bit to the left because it now also has these extra elements. And now, every time we repeat again, it's not going to change any of the elements. So we've finished everything. It doesn't matter. So he's clicking the update centroids, but it's not changing any elements closest centroid. So it's not updating the centroids locations. All of the centroids are now staying in their same position. I think that demonstrates it quite nicely on how it slowly moves it to the centers of the centroids. Okay. So this is the second last thing, k-means plus plus. So one of the things we had to do here is we picked, at the very start, we just picked 3 random positions. However, some positions are going to lead to different results than others, so we want to pick them smartly. And the way we do this is by making them as far away as possible from each other while still being random. So it's, I don't know the correct way to word this, but if it's not random, then it might always I don't really know how to explain it, but essentially, I don't know if anyone else knows how to explain this better than me on why we wouldn't want it to always be in the same positions. If not, we can just continue, and you can just kind of know you don't want it to always be random. Sorry, you don't want it to not be random, because if it's deterministic, then it might not give you the right results you want. We can just continue, but just no, you don't want it to always be deterministic. So the first thing you do is you pick a random element, and then we're going to continue. So we pick k for the first one, we'd pick a random place. Now for the second one, we would still pick it at random. However, we're going to weight the randomness based on its distance from their closest centroids. So let me set it k means plus plus. So if we pick a random element to be our starting position, let's say we pick this one, we're going to pick the next element randomly, but it's going to be weighted with its distance. So every element, because we've only got one cluster right now, every element, its closest cluster is this one, because there's only one. So this one is still going to have a chance of being picked, but this one's going to have a lot higher chance of being picked. I think so we take its closest centroid, the distance to its closest centroid, and we square it. And squaring is exponential well, you know how squares, it goes up exponentially. So 5 squared is significantly larger than 2 squared, even though they're just 3 apart. So this one would still have a chance of being picked, but not compared to this one. This one would significantly have a high chance of being picked. So let's say it ends up picking this one. So we now have 2 centroids. We got this one and this one. So let's say k equals 3, so we want 3 clusters. We're going to do it again. But now, this element's closest centroid is this one. This element's closest centroid is this one. So all of these ones are closest to this. And all of these ones are closest to this. So now, because we have a centroid here and a centroid here, the furthest away ones are going to be up here. So these ones have the highest chance of being picked compared to these two. Sorry, like these down here, because these are all quite close to a centroid. And in the end, we're going to end up with, on average, 3 faraway clusters. It could happen that we get some close ones, but on average, they're going to be far away from each other. So that's what k-means plus plus does, and it's just an algorithm for picking our starting clusters. So the way we write this, the way you kind of write about this formally is you say we pick the next centroid to be at a random element. However, its probability of being picked is proportional to the distance to its closest centroid squared, which just basically means it's more likely to pick the further away elements as the next centroid. And we just repeat that until we've got k centroids. So if we had 5, we'd pick one at random. Let's say we pick this one. We're going to end up getting another one, and we just repeat, and then we've got 5 centroids, and we're ready to do the k-means algorithm. I hope that all makes sense. Okay, the last thing we need to do is talk about choosing k. So here we've sometimes used k equals 3, or just then k equals 5. But it's quite an arbitrary thing. So there's different ways you can think about picking k. The easiest way is if you have prior domain knowledge. So you might know you want 2 groups. You might want high-performing employees and low-performing employees. That's 2 distinct groups. So you already know k from the very start. If you don't have prior domain knowledge like that and you don't know how many clusters you should use, you want to use what's called, you don't want to, but you could use what's called the Elba method. And what we're going to do is we're going to run the k-means with differing k's. So we're going to use k equals 0. Sorry, that wouldn't work. K equals 1, k equals 2, k equals 3, all the way up to 20. Probably using the k-means plus plus algorithm or something like that, and then taking the average on multiple goes. And we look at the WCSS, which, remember, WCSS is the sum of all of the inertias, and the inertia tells us how compact a cluster is. So the WCSS tells us we're using as a way to kind of rank how well our clusters are and how compact they all are. And we just do this with all our different k's, and we look what's called for the Elba point, or the inflection point, which is where it starts to flatten. So we can see our WCSS is significantly going down. But we don't necessarily want to pick when it's as low as possible, because if we did that, then it's just going to end up being every element is in its own cluster, then the WCSS would be 0. We talk about why this works here. I didn't write it. So here's the intuition behind the Elba method. So if we assume there's k star distinct clusters in the observed dataset, when k is less than k star, so k star is our correct, the amount of clusters within our thing. If we're choosing k and it's less than our actual cluster amount, the clusters returned by k-means will each contain a subset of the true underlying clusters. Consequently, this means the WCSS tends to decrease substantially with each successive increase in k until it reaches our k star. So when we have k equals 1 here, or k equals 2, and then we compare it to k equals 4, the decrease is large. And that's because natural groups are successfully assigned to our separate clusters. Once we go past our k equals star, so k star is the correct amount of clusters, one of the clusters estimated by k-means must partition into at least one of the natural groups. At least one of the natural groups are going to partition into 2. And this is going to provide a smaller decrease in our WCSS, so our sum of inertias, as k is further increased. So k equals k star corresponds to the number of clusters where there is a sharp decrease in successive differences in our WCSS. So once we notice that it's not substantially decreasing anymore, that's how many clusters we want to pick. Does that all make sense? Just a lot of words there. Okay. So here's some, I didn't write about this in my paragraph, but some other limitations of a k-means. It's going to have problems when outliers are present, because we're always taking the average centroid. If we have an outlier, then it's going to substantially it's going to shift it in its direction. So they can influence the clusters quite a bit. And then this increases our WCSS, and we can't. So our WCSS is going to be a bigger value, so we might be looking at it thinking like our cluster isn't as good as it should be, just because if this element is outside by itself, it's not going to get any closer unless it has like its own cluster. But if you have like 2 clusters, then you can't give it to this one outside, so this one's going to end up dragging up for WCSS. It also has problems when clusters are differing, so the densities. Here we've got quite a big range of points, and then also we've got 2 smaller clusters. If we're using 3 k-means clusters, this is going to end up, if we look here, it's kind of combining these 2, because their densities are so small compared to this one. The WCSS, the way it's being calculated, is not kind of built for that. So it ended up, in this example, creating 2 clusters out of these big ones and combining the small densities ones. And non-globular shapes. So our centroid is kind of, when we're calculating the distances to our centroid, it's kind of best fitted for it to be a circle around the centroid. So if we've got something like, let's say like an oval, it's not going to work as well. Because, yeah, the clustering is calculating the distance. So it works better when everything's close by. If you have something like a fat oval, the distance is going to be even greater at the sides compared to go straight up and down when there's no points. And we could just look at the applications real quick of k-means. A key tool in the area of image and signal compression, vector quantization. I mean, I don't know how much, if you guys even care much, but I didn't put these in my PowerPoint. Vector quantization. So we break these images down into smaller blocks and run the algorithm on that. I mean, I haven't looked at this, so it's probably not much help me going through these last bits, because I didn't include it in my PowerPoint, because I was meant to be doing the whole thing today, so I skipped over it. But if you guys want to have a look at this in your own time, that's probably going to be more helpful than me trying to read it now. But yeah, that's pretty much all I had planned for today. I think, yeah. So if you have any questions, or if that's it, then you can go, I guess. Okay. I think that's it then. Goodbye.